Section 8.1, Lewis dot symbols. So now what we're going to do is we're going to look at how we can describe chemical bonding. This chapter is dedicated to the issue of explaining the chemical bond. So we're going to begin with a breakthrough idea, which was developed by G.N. Lewis back in the 20th century. And his idea was this, that if you consider the issue of stability in an atom, his claim is that stability can be reached when the atom becomes isoelectronic with a noble gas. Isoelectronic with a noble gas. That stability comes from that achievement, that attainment. Okay, it's a very powerful idea. So when we say stability, what we mean is the atom will become less reactive. So for example, if you consider the sodium atom in water, sodium will react violently with water. Normally we don't think of water as being particularly reactive, but it turns out the sodium atom is very reactive in water. When it reacts with water, essentially what happens is the sodium atom loses an electron. So the sodium atom has 11 electrons. It's atomic number 11. And so if you look at its electronic configuration, 1s2, 2s2, 2p6, 3s1, there's our 11 electrons. Essentially what happens is sodium reacts with water to lose one of its electrons. That would be oxidation, right? Just to bring it back to an earlier topic, back from chapter 4. The loss of electrons is oxidation. So essentially what sodium does when it reacts with water is it loses this electron right here. Its outermost electron, which we call a valence electron. The valence electrons are the electrons that are in the outermost shell of the electronic configuration of the atom. So if you take a look, 1s2, 2s2, 2p6, 3s1, 3 is the highest principal quantum number, so that's the outermost shell. So that would be called the valence electron. There's only one electron in sodium, right? That's in the valence shell, in the 3s subshell. These would all be called core electrons. So if we consider the core electrons of the sodium atom, 1s2, 2s2, 2p6, if you look through the periodic table, what you'll find is that's the same configuration as neon, element number 10. Right? Neon is 1s2, 2s2, 2p6. So what we would say about the sodium atom is the sodium atom has a configuration of neon. It's the same as neon, but it has an extra electron in its valence shell, which we'll call 3s1. These would be the core electrons. Okay. Now notice there's some square brackets here. The square bracket notation is all about indicating that when we write Ne, we mean that that's the electron configuration in neon. We're not saying that sodium is the same thing as a neon atom. We're just saying it has the same electron configuration as neon, so we use the square brackets to indicate that, but it has one additional electron in its valence shell. right here. So these are valence electrons. Now there's only one valence electron for sodium, but if that was a 3s2 and then 3p2, those would all be valence electrons. So here's what happens. When you remove the outermost electron, when you remove the valence electron from a sodium, which is exactly what the water does, the water takes an electron from the sodium, you're taking out the valence electron. So the sodium becomes a sodium ion, Na+, by losing an electron. And so the sodium atom has an electron configuration of neon 3s1. The sodium ion just has a configuration of neon. It's lost its valence electron and becomes configuration of neon. Now notice that sodium ion, which by the way is very stable in water, the sodium atom is very reactive in water. The sodium ion is isoelectronic with neon. So this term, isoelectronic, what that means is they have the same electron configuration. Okay? Same electron configuration. That's what's meant by the term isoelectronic. So that means the sodium ion is isoelectronic with the neon atom. And according to Lewis, G.N. Lewis, when an atom becomes isoelectronic with a noble gas, it becomes more stable. And so we would argue based on this that in water, the sodium ion is stable, but the sodium atom is unstable because the sodium ion is isoelectronic with the neon atom. Okay? That's the idea of isoelectronic. A powerful claim by Lewis. And evidence suggests there's a lot of truth to it. We'll see this. Now, to take us to the next step, we're going to talk about Lewis's dot symbols. What Lewis recognized is that if you take the electron configuration of an element like boron, boron is element number 3, so its electron configuration is 1s2. I'm sorry, boron is number 5. Lithium is number 3. 1s2, 2s2, 2p1. That we could use this notation, this noble gas kernel or core configuration. Helium is element number 2, so it's 1s2. So boron would be helium, 2s2, 2p1. And so now this is the outer shell, n equals 2. So we would say that it has 3 valence electrons. And what Lewis noticed is that we could represent these valence electrons as particles. Okay, now recognize the electron. We talked about that in chapter 6, that we normally think of the electron as a wave, right? But it does have particle-like properties, right? It's really duality. We're not saying it's just a wave. It's actually a wave and it's a particle. That's the duality. That's the mystery of it. So what we're going to do is we're going to represent those valence electrons, not the core electrons. Remember, these are the core electrons. We're going to represent the valence electrons in the following way. The nucleus of boron, okay, and the core electrons are represented like this. The symbol represents the nucleus of boron. Remember, that's where all the protons and neutrons are. and the core electrons. Okay? Then we represent the valence electrons as dots written around the symbol. So these are valence electrons. Okay? So the idea here is that the nucleus of the atom and the core electrons are represented with the symbol of the element. And then the valence electrons are represented with these dots that, as you can see, are distributed individually around the symbol. Okay? Let me show you another example. Let's say that we're discussing the element calcium. Okay? Calcium is element number 20. So it has an electron configuration 1s2. I'm going to go through this whole thing, but as you practice these, you get better and better at doing them quickly. Okay? 20 electrons, right? 2, 4, 10, 12, 18, 20. Calcium. Didn't quite get into the 3D subshell. Now, let's first identify which are the core electrons and which are the valence electrons. These are the core electrons right here. There's 18 of them, right? And actually, if you did the noble gas configuration, you would find that that would be, those core electrons would be isoelectronic with argon. Argon is element number 18. But we have these outermost electrons. The highest value of N in this configuration is 4. So that means these are the valence electrons. So there's only 2, right? We have a core with 18 electrons, and we have a valence shell with 2 electrons. So here's what we do. We represent the nucleus of the calcium atom and its core electrons, all 18 electrons, with the symbol of the element. Just the symbol. And then we indicate the 2 valence electrons as individual dots that are drawn separately. Okay? There you go. So this would be called a Lewis dot symbol. Okay? So let's try one more. This time, you can try it yourself. You can pause the video if you want and try it. It might be helpful to have a periodic table for you. Okay, so let's try fluorine, which is element number 9. We're going to draw the Lewis dot symbol. Okay, so you could try it yourself. See what you come up with. Okay, let's take a look. Fluorine is element number 9. So 1s2, 2s2, 2p5. So now the outermost shell is n equals 2. So those are the valence electrons. Now how many valence electrons are there? There's 2 here and 5 here. That's a total of 7. So we're going to have 7 dots. These are core electrons. We're not going to represent those in the Lewis symbol, in the Lewis dot symbol. So here's what you do. You represent the nucleus and the core electrons. There's only 2 core electrons. And then we represent the 7 valence electrons like so. There's 4. And notice what I'm doing. I'm going around almost like thinking of it like a box. So 1, 2, 3. Each side gets an electron. But we got to do 7. So what do? Every time, once you get around those square, once you get around the box, now start adding a second one to form a pair of electrons. So there's 5, 6, 7. So it's normally written like this. 7 valence electrons. Okay? So this would be the Lewis dot symbol. And generally, you don't have to go beyond 8. 8 would be the most that you would have to draw in here, most likely. We'll take a look at, when we get to Lewis structures, at how that works, but that would be the Lewis dot symbol for fluorine. So those would be representing the valence electrons. There are 7 valence electrons. Now, I want to show you the pattern of what happens. And so I'm going to come out here to this figure from your textbook. These are the Lewis dot symbols for many of the elements. Let me make this a little bit bigger. Notice the first 2 columns are shown, the alkali metals and the alkaline earth metals. The transition metals are not shown. How come? The reason actually is that Lewis structures are not a good way to analyze transition metals. The chemistry and the physics of transition metals is such that Lewis structures are just not that helpful. They don't explain much. Okay? Now, to the right, where the nonmetals are, by the way, the blue colors that we're seeing here is a way of describing what we call main group elements. It's a way of categorizing. So the alkali metals and the alkaline earth metals and the metalloids and the nonmetals are often referred to as main group elements. So take a look at boron. We did boron, right? And we did fluorine. And we did calcium. And what I want to draw your attention to is that if you take a look at one column, one family is the term we use. For example, the alkali metals. Column 1A, far over to the left. Do you notice that although the symbol of the element changes, the number of dots stays the same? There's 1 dot for all of those elements in the first column. And that's because all of those elements only have 1 valence electron. And so that's very useful for us. It gets us not having to draw out the entire electron configuration of the element. All we have to know is that if the element is in the first column, it has 1 valence electron, right? For hydrogen, the valence electron is 1s1. For lithium, the valence electron is 2s1. For sodium, it's 3s1. So they're in different shells, but it's still the same number of valence electrons, therefore the same number of dots. So that makes this very easy. Column 1, 1 dot. Column 2, 2 dots. In fact, if you use the old notation on the periodic table, the ones that have the A's, 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A for the main group elements, that number is the number of dots. So for, let's take calcium. Calcium is in column 2A, 2 dots. Aluminum, it's in column 3A, 3 dots. Fluorine, it's in column 7A, 7 dots. So the Lewis dot symbols are easy to draw for these. You just have to look at where it is in the periodic table. Very, very nice. Okay? Now, I do want to talk a little bit about ions because we looked at this idea early in this lecture, early in this video, about the stability of ions, right? I made the claim that sodium loses an electron to be isoelectronic with neon, right? So now what I want to do is I want to show you a nonmetal, what happens. Okay, let's take oxygen, for example. Oxygen is in column 6A. So that means it has 6 valence electrons, right? So I'm no longer drawing the electron configurations. I don't need to. All I got to do is look at that periodic table and find oxygen. Oxygen is in column 6A, so it has 6 valence electrons. So 1, 2, 3, 4, 5, 6. Now sometimes you'll see where they put 2 dots and where they put 1 dot. That's not that important. The point is that you have 2 pairs, and each pair is on a corner of this box, and then you have 2 individual dots, right? 2 individual valence electrons. Okay, so there's your Lewis dot symbol for oxygen. Is it isoelectronic with neon? The next element the element that is closest to oxygen in the periodic table that's a noble gas. Neon is all the way to the right in column 8A. Look at neon. Neon has 8 dots. So what we would claim is that oxygen might become stable by gaining 2 dots, by gaining 2 valence electrons to become isoelectronic with neon. So here's what we would claim, that oxygen could gain 2 electrons in a reduction half reaction. And so here's what would happen. If you gave it 2 more dots, now it would have 2 dots here, right, on the left, and 2 dots here at the top. It's now got a charge of -2, right? By gaining those 2 electrons, it's -2. And we would claim it is now isoelectronic with neon. Okay? So nonmetals tend to gain electrons, right? To become isoelectronic with the noble gas that's in that period, in that row. Okay? So oxygen gains 2 electrons, becomes isoelectronic with neon, and we represent that with our little dots here, our 8 dots. Now, what about metals? Again, metals, sorry. These have a tendency to lose electrons. Okay, so let's try it with potassium. Potassium is element number 19. If you look in the periodic table, potassium is in the first column. It's in the alkali metals column. Has 1 dot, only 1 dot, right? Has a tendency to lose electrons. That's oxidation. Lose 1 electron. Look what happened. We took the dot away. It doesn't have any dots anymore. Why no dots? Because there was only 1 valence electron to lose. So potassium tends to lose 1 electron, whereas oxygen tends to gain 2 electrons. So why K+? What's stable about K+? Well, K+ has 18 electrons because potassium has 19 electrons. 18 core electrons, 1 valence electron. So now the potassium ion only has 18 electrons. They're all core electrons. It has become isoelectronic with element number 18, which is argon. Argon has 18 electrons, right? So take a look at the periodic table. Your potassium here loses 1 electron and becomes isoelectronic. Becomes isoelectronic with argon by losing that 1 electron. Isn't that amazing? So Lewis was onto something. He was onto something so powerful that we're going to use it for pretty much the remainder of this chapter. And our discussion of chemical bonding is essentially based on this idea of stability of an atom based on the idea of having the same or similar electron configuration as a noble gas element.